In this lecture, we will be covering harmonics imaging. To understand fundamental and harmonic frequency, we need to first know what fundamental frequency is. So that is the frequency of sound that is created by the transducer and then transmitted into the body. This is what our transducers are labeled as and what the sound frequency that they emit out. Harmonic frequency then is considered to be twice the fundamental frequency. Remember that, twice the fundamental frequency. So for example, if a transducer transmits a sound pulse with a fundamental frequency of 2 megahertz, and we are introducing harmonic imaging mode, then the image is only going to be created from 4 megahertz sound reflections. So again, second harmonic frequency, the probe is a 2 megahertz probe. That is what is sent into the body. But then the transducer and the machine are only going to listen for frequencies that come back at that 4 megahertz. So all of this might seem kind of strange. How is the machine sending out this fundamental frequency but only listening for that harmonic frequency? So that's kind of what we're going to cover in this lecture. So that fundamental imaging is created by only listening for fundamental frequency reflections. Fundamental imaging is really good for penetration, not so good for superficial imaging, and it's also at kind of that mid-range depth of imaging. So fundamental sometimes really helps us out with getting that sound beam really far into the body. When we use harmonic imaging though, it just kind of cleans up our picture. And what it tends to do is clean up our picture in that mid-range. Harmonic is not as good for imaging deeply into the body, but more into that mid-range. It's poor for superficial, it's poor for deep, but really good for mid-range imaging. And it turns out that that is where harmonics are created. So as the sound is traveling through the body, their mid-range tissues are creating harmonic frequencies, and that is what is being sent back to the transducer. So at that point, the machine can listen for frequencies that are coming back at twice the speed or twice the frequency of our fundamental imaging. So our first example on top here is a thyroid, and on the left we are using fundamental imaging, and on the right we are starting to use tissue harmonics. We can see that the borders just get a little bit crisper, everything cleans up a little bit, we're reducing kind of that background scattering of sound and really getting nice information back from the thyroid. We can see with the heart that we're getting the same thing as well. On the left is our fundamental imaging. We're seeing kind of blurry borders, not really able to evaluate the wall very well. Where on the right we are using tissue harmonics imaging, and that has really cleaned up our borders, made our valves very obvious, made the wall very obvious, and we can just evaluate everything a little bit better. So that's in the end really what tissue harmonics is doing. It just helps us to evaluate structures better because we are getting a clearer sound. So with harmonic imaging, you may see it referred to as second harmonic. And it's important to remember that harmonics are created in the tissue. They're not created in the transducer or receiver, they are created in the tissue, because as the frequency components of the sound pulse enter into the body, they actually end up changing a little bit as they increase their depth of ultrasound penetration into the body. There are two types of harmonics in ultrasound, the first one being tissue harmonics, which is mostly what we're covering in this lecture. And tissue harmonics are going to be created during transmission. So as the sound travels into the body, tissue harmonics are created. This occurs because of the interaction of the ultrasound and the tissue. The ultrasound pulse frequency is going to change as it moves into the body. The further it goes into the body, the more harmonics are produced. And in this case, the tissue does not resonate, rather the sound beam starts to distort. There's also a second type of harmonics called contrast harmonics, which we will cover more in the next lecture. So as I was saying before, when we use harmonic imaging, that sound beam starts to distort a little bit. So typically with fundamental imaging, And in the beginning of harmonics imaging, our sound beam is going to have a very smooth sinusoidal waveform. It's going to be very even, predictable, and symmetrical. We consider this to be linear behavior. Nonlinear behavior is what actually causes tissue harmonic imaging to happen. It's going to be an uneven, disproportional, and asymmetrical type of waveform. And this is what gives rise to harmonic frequency. So remember, nonlinear behavior equals harmonic frequency. What ends up happening is the sound beam travels into the body, and it starts to travel at uneven speeds through the soft tissue. And this is going to alter the shape of the sound beam. It's going to travel just a little bit faster through the compression part and just a little bit slower through rarefaction parts. So we'll start to get an uneven, nonlinear waveform created. There's a small amount of energy that's transferred from that fundamental frequency to the harmonic frequency. And so because of that, you need a strong fundamental beam to create just enough harmonic frequency. And with that, the strength of harmonic wave is going to grow a little bit as the sound travels into the tissue. The deeper that the harmonic frequency is being created, the more distorted the wave becomes and becomes less able to create images, which is why harmonics isn't very good for deep imaging as it is for mid-range imaging. So again, linear behavior is very predictable. It's a straight line. It comes on time, just like the subways do. It is all very predictable. Linear behavior does not create harmonics. It is when that sound beam travels through that tissue and starts to become nonlinear or unpredictable as to how it's going to happen is how that harmonics waveform is created. So remember, nonlinear equals harmonics. Some other things that you need to know regarding fundamental versus tissue harmonics is fundamental imaging is going to cause a significant amount of artifact to arise within the first few centimeters of tissue. This is where most of our strong artifacts are going to occur because there are so many different layers of superficial tissue that the sound beams hit it, start bouncing back and forth between one another, start scattering everywhere. It just kind of distorts that first few centimeter or first centimeter or so of our image. Where tissue harmonic imaging, there is no distortion right at those shallow depth. It kind of gets a free ride through those superficial tissues. It's only once it gets a little bit further into the tissue that they do distort and create that tissue harmonics. So this graph kind of helps us to show how all of this works. So as that frequency comes in, again, we're getting that really nice, smooth, predictable waveform right in the near field. So this has little to no harmonics generated in that near field part. Again, the waveform is getting kind of a free ride through these first centimeters up here. It's really once we get into the midfield that we start to get that speed up in compression and slow down in rarefaction. That nonlinear behavior is what is causing our harmonic tissue frequency to be generated, and this is where we're going to get our best harmonic effects. As that sound beam travels further into the body, we are going to see even greater speed ups during the compression and greater slowdowns during rarefaction, but the harmonics is going to attenuate faster than it's produced in this far field, and we're just not going to get as clear pictures from that far field part. So really harmonics is best for this midfield. It helps for the far field, but just not as much. So in the end, harmonics does improve our imaging. The harmonic beam is very narrow. When we have our main sound beam coming out, harmonics is only created from a very narrow slice of the middle of it. You need a very strong sound beam to begin with. So this original sound beam has to be very strong. And then our harmonics beam is created from the strongest part of the beam and ends up being very narrow. So when we turn harmonics on, we are improving our lateral resolution. So remember, a narrow sound beam means that we can get better side-to-side resolution. Also, when we use harmonics imaging, we're going to reduce that grading lobe artifact. Weak signals cannot create harmonics, so all those little grading lobes that were maybe coming off the side here, none of these are going to be creating harmonics, so we're not going to get any information really back from that. The machine's not even going to recognize that they're sending information back. And then typically, our harmonic sound beam is not affected by artifacts because all that superficial reverb is eliminated in the top of our pictures. So this all looks much cleaner than it does with just the fundamental imaging because we're not getting distortion harmonics from up there. So when the sound beam is being transferred into the body, again we have our transducer at 2 megahertz. The fundamental frequency is what is sent into the body because harmonics isn't created until it gets into the tissue. So we have to figure out how we are going to isolate that harmonic information. And there's a few different ways that the machines do it. It used to use more of a bandwidth filter to keep the fundamental and harmonics separate, but ended up not being very efficient. We couldn't keep up with the rate of sound going into the body and coming back to produce quality ultrasound pictures. So now the two ways that we isolate that harmonic frequency is either through pulse inversion harmonics or power modulation harmonics. So this picture kind of shows us a little bit more about what we're trying to do. With fundamental imaging, our transmitted frequency going into the body is 3.5 megahertz in this example, and all the machine is going to want to listen for are any frequencies that are coming back at 3.5 megahertz. So it's going to be listening for that fundamental frequency as it returns, and it's going to treat any other frequency just as noise, and so we need to get rid of that noise somehow. When we use harmonic imaging, the transmitted frequency may be 3.5 megahertz, but now we're only going to listen for any received frequencies at 7 megahertz, again, twice the fundamental frequency. So now the machine needs to ignore anything coming back other than 7 megahertz and needs to treat it all as noise. But we need to figure out how to get rid of that noise so it doesn't distort our picture. So that is where pulse inversion harmonics and power modulation harmonics come in. So with pulse inversion harmonics, a fundamental frequency will be sent into the body, and then we send a negative fundamental frequency also into the body. So a sound wave that will exactly cancel out our fundamental frequency. So that gets sent into the body. And then what ends up coming back is just our harmonics waveform. So we send, we'll say, a positive fundamental frequency out, also a negative fundamental frequency out. So those two cancel each other out. And now the machine can only hear that harmonic frequency coming back. The other option is power modulation harmonics. This one is not as popular as pulse inversion is, but it is another way to isolate that harmonic frequency. So with power modulation harmonics, a sound beam is sent into the body, one that's a little bit weaker, and then a very strong sound beam is sent into the body. Again, that strong sound beam is going to be the one that's going to create the harmonics imaging. As those sound beams come back, the very strong sound beam is going to come back along with the harmonics, and that very weak, or the weaker one, is also going to come back to the transducer. What the machine will do then is take that weaker one, which happens to be half as weak or half as strong as the strong beam, and double it. So now we have a doubled frequency to match that strong frequency that we had originally. And what they will do is end up canceling out each other. So in the end, the only thing that the machine will hear are the harmonics that are coming back. So again, with power modulation, remember that it is a strong beam and a beam that is half as strong. That half as strong beam gets doubled. So the fundamental frequencies then are canceled out, and all that is left is harmonics imaging. So the important parts of harmonics imaging, remember that it is twice the fundamental frequency. Remember that it happens within the tissue and that it is best utilized at the mid-range area of our picture. There's no distortion in the shallow part, so we don't get harmonics there. And as we get deeper into our imaging, great harmonics is created, but it starts to attenuate too quickly, and so we don't get really as good of information from deep fields for our imaging. So really, the mid imaging is best for harmonics. It cleans our pictures up, it makes our blacks a little bit blacker, crispens up borders, and is really ideal. If we can use it, we should be using it for our pictures. So also remember that we need to isolate the harmonic frequency, and that we do that through pulse inversion or power modulation. Pulse inversion is the more utilized way to isolate that harmonic frequency. And just remember that pulse inversion is using a positive and a negative waveform to cancel one another out, so harmonics is left, where power modulation uses a strong and a weak waveform, doubling that weak waveform to cancel out the fundamental frequency. So in the meantime, let's go ahead and test ourselves. Number 1, if the fundamental frequency is 5 megahertz, what is the harmonic frequency? Is it A, 2.5 megahertz, B, 5 megahertz, C, 10 megahertz, or D, 15 megahertz? Number 2, where would the greatest amount of harmonics be created? A, before entering the body, B, 1 centimeter into the body, C, 4 centimeters into the body, or D, 15 centimeters into the body. And number 3, harmonic waves act in blank ways. Is it A, predictable, B, nonlinear, C, symmetrical, or D, even?